Thank you for attending our last session for automated buildings. Appreciate you being here today.
Yeah, thanks for coming. Yay. You could move forward if you really wanted to, since there's, 20 of you, but.
I'm Scott Cochran, president of Cochran Supply. I've done a few intros, so a lot of you have probably heard this, but 25 years in the industry, second generation, and we've been having a lot of fun here the last couple of days, and we're excited to finish off here. So,
I got the less cool mic, that's fine. My name is Stephanie Poole. I'm a principal with SES Consulting. So we're a consulting engineering firm. We do mechanical and controls design. Some of you have probably heard our other sessions, so I'll keep this brief. But we started out with controls, and then we kind of transitioned to mechanical design. So we do, can you hear me? This is fine, right? Yeah. Okay. We do a lot of, decarbonization, big systems, heat recovery systems, and then a lot of recommissioning of existing systems that have been not commissioned properly in the first place, and also recommissioning just kind of standard. So we're going to talk to you today a little bit about energy management. Now, we have some slides prepared, but there's a small group. So if you have questions, we can totally take this in a different direction. We can make this very interactive. All right, I guess I am controlling these. This is you, Scott.
okay, so we, as the mechanical control industry, we are a huge amount of the actual energy used in the United States. Between us and lighting, we make up almost half of the energy used. And of course, energy, remember, that includes construction, that includes manufacturing. So we are energy pigs, effectively. And frankly, a ton of this energy that we're using in buildings today, we don't have to. And we know it. So there's huge potential savings for your customers or for yourself if you're a building owner by trying to focus on reducing or making these applications more efficient within your buildings.
Next one's you too, so you can keep going.
Okay. So when we look at a building and we look at the utilities that they're using, oftentimes, we focus on maybe, just electricity. But realistically, if we're going to look at a building's usage, we have to get all the energy that it's using together. And to do that, we need to look at the different types of utilities we're working with. Of course, the electrical utilities in the United States is deregulated. And so depending on where you are, you're going to have a different electrical or gas or whomever provider. These providers have different ways of billing their customers. They have demand charges, they have taxes added, they have all sorts of excise taxes and other rates that they add. And so when we look at utility billing, typically we're looking at it in a denominator called kWh. Do most people in here understand what kilowatt hours are? Let me explain real quick. So a kilowatt is is essentially a unit of energy. And when we look at it at a kilowatt hour, what we're really asking is how many units are we using in an hour? Okay. And that would equal our kilowatt hour as a consumption number. So when you get billed, essentially it's time-based billing, right? So it's what is your quantity in this time frame? And then they give you a rate, and depending on the utility, you get different rates. Right now, I live in Detroit. The current street rate, I think, is down to maybe 12 cents per kilowatt hour. But this rate varies in the United States. I've seen rates as high as 25 cents per kilowatt hour. I've seen rates as low as 7 cents per kilowatt hour. It really depends on which state you're in. And then this rate is typically applied against a meter, and the meter is really getting your quotient over time. Now, natural gas is a different type of median, of course, but it's still billed in a very similar manner, where instead of using kilowatts as the unit of measure, we're using BTUs, British thermal units per hour. And then, of course, water and sewer. that gets billed in a different rate, which is gallons per minute, GPM per hour. So in order to look at a building's full energy usage, though, you want to try to figure out a way to combine all three of those utilities or more, and then convert the different rates into a common rate or a common measurement like BTUs, and get down to essentially a way of understanding what is essentially how much energy per square foot am I using in a building, okay? And I can help, you can all use Google now, and it'll give you the conversions of all these real quickly, okay? So whenever you're trying to baseline or figure out how much energy a building's using, you want to collect all those bills, transfer it to a single unit of measurement, and then get their square footage and come up with a number as an example of a way to do it. Does that make sense to everybody?
I'll just add a little bit about the peak demand charge too. Like we have clients that like to deal with it in different ways. If I'm doing an energy study, I'm going to break down the demand and the kilowatt hours, so the kilowatts and the kilowatt hours separately, and combine those two costs. And there's some times where we installed this big heat pump, and so our kilowatt hours went way, way down. We're saving a lot of that, but our demand charges went way, way up. And so you don't want to forget about that. We want to look at both of them because, your peak demand charge can be pretty significant if you're running a bunch more electrical equipment. So something to keep in mind. I do have clients who are like, I'm not going to break it out, and they'll just kind of do like a combined rate of kilowatt hours that includes the extra demand. So you can do it either way. Most consultants will probably break it down just to be more accurate, but it's definitely not a safe assumption that if you decrease your kilowatt hours, your overall costs will decrease, because you really got to watch those demand peaks as well.
Yeah, and could you go a little bit more into demand peaks? Like what are they literally, and how do they affect their rate? Yeah,
so depending on what rate you have, and I'm from Canada, so I'm hoping these are mostly the same, but typically you have your 15-minute average, and so it'll bill your kilowatts at 15-minute averages. Now, if you're a small, like a house or something, you're typically not charged demand, so that really doesn't matter to you. That's the same in the States? Yeah, okay, cool. But otherwise, if you're a bigger system, you're going to be charged your monthly rate. It's basically the highest 15-minute average you use, that's what you're getting charged. So if you use that high 15-minute average once a month, doesn't matter. You're getting that charge. So that's why it's so important to watch these, because, we'll do a lot of what's called demand response. So it's like, okay, I know that in the summer, my peak demand typically is in the afternoon when all my cooling systems are kicking on. So you can do a demand response where you're like, okay, if I'm starting to hit my thresholds, and you'll have like a lower threshold, which is like, okay, start doing things a little bit. And then the higher one, which is like, oh crap, we're like really high. Let's like really drop things. And you can do it based on a trigger point. So it's like, if it reaches this point, do things. So maybe ramp the fans down to 75%, or relax the set points a little bit, or turn down the pumps, or if you can turn off some spaces or some lights, maybe you can do things like that. The other way to do it is more of like a load management. So it's not like a response to a trigger, but rather a more like I'm pre-planning for it. So an example would be in a building where I have electric heat. Typically, my peak is probably going to happen first thing in the morning, right? I'm warming up my building, everything's cold, my electric boiler or my electric heat pump is on. And so my peak is going to happen then. And I know it's always going to happen then. I don't need to be like, set a threshold and drop it. Like I always know, so I can plan for that. So some of the things we'll do is like, okay, we had a heat pump system where it was like the heat pump was being used for morning startup, and it was struggling, and it would run for 2 hours, and it wasn't able to heat up the building, because heat pumps, they don't like cold water temperatures, so they don't like cold starts. So what we did, what was happening is the heat pump was running, and then at 8 o'clock, the heat pump still hadn't heated up the building, so the boiler would come on. And 8 o'clock is like when everyone's in the building, everyone's turning on their computers, and that's when the peak was. So this like huge boiler load is being added to the existing peak, and their demand charges were through the roof. So what we ended up doing is we're like, okay, the boiler's coming on anyway because the heat pump can't cold start. Heat pumps, they really don't like situations where you're starting really cold. So what a good strategy is now we're turning the boiler on at like 6, and we're turning it on for, half an hour, depending on how cold it is outside. So that's not when any of the other peak demands are. So we're shifting it back. So that's not adding to your peak demand charge. And it's also helping. So the boiler heats up the loop a little bit. And now the heat pump's like, yes, I like these temperatures. I can operate the rest of the day with this temperature, but I couldn't cold start. So that's how you can kind of shift that. And so that's more of a load management strategy in a like, I know when my peaks are, I'm going to update my sequences and the way I run my building so that my peaks don't all stack on top of each other. Whereas a demand response is in triggers to like, one of your utilities is like, hey, this is a peak, I need you to drop now. Or you look at your peaks and you drop. So it's in response to some external piece as opposed to kind of like a general change in strategy to ensure that your peaks don't all stack. And you can do that like if you had a bunch of air conditioners in a building, you could stagger them so they can't all turn on at once. It's like, some of them turn on, maybe the ones that are farthest from set point, they would turn on. And then once they're like, 2 degrees, then they turn off and they let the next ones turn on. And so you can kind of stagger that load so that you're not getting it all at the exact same time. And that will end up saving like a lot because peak demand charges can be really significant if you have a lot of electrical load.
Fair. And to add on that, if you really dive into the utilities and give them crap about it, because you're like, hey, man, I only use that much for what, like a minute? Like, come on, man. Why do you got to charge me so much? What they'll tell you is, look, man, I got to put that much on the wire for you then at all times. Because I'm assuming you're going to, you might have to use that at any given time. And it costs me more to have that much power available to you. So we can't really knock them for it. They got a good reason why they do it. But to Stephanie's point, it can jack your bill because like, one bad day and man, you're paying that rate for a long time. So you got to be careful, right? Like, I don't know. I've seen people do some pretty drastic things to avoid it. There's what we call manual load shedding. Turn that chiller off.
Yeah. I mean, I had a client, their university in like Eastern Canada, and they have cogen systems. And what they'll do is during peak demand, they'll turn off their electric heating systems and they'll run gas. And obviously the GHG associated with that is not like they're spending more, but they ended up saving $1 million over the course of a year in doing that. And then they put that $1 million to other, strategies to reduce emissions or like help the space. So it can be pretty significant if you have a big load.
Yeah, as a controls guy, what we don't recommend is automatic load shedding. So you put a real-time meter on a building, and then you look at the amp draw, and then based on that, you actually have your system automatically shut off equipment to alleviate the demand charge. I've seen that done, and of course, whose unit do they turn off first? The president of the company. Right? So, but no, more importantly, your equipment is not made to just be turned off in the roughest conditions. It's kind of like you're in a hurricane on your boat and you say, oh, turn the boat off, man. That's not a good move. And it's the same thing. Load shedding is something that should be worked with your engineers. There should be a strategy in advance. It should be tested. It should be understood. Just keep that in mind as well.
Yeah, one other thing, just because we're going down the load shedding rabbit hole, like one of the things to consider is if you're load shedding, like it's really, really hot out, right? So you're load shedding, you're relaxing set points, you're turning things down. What do you think is going to happen when that load shedding strategy stops? Well, now everything's going to peak, and it's going to be like you didn't reduce your peak, you just shifted it, so you're still paying the same amount, because as soon as you relax that strategy, all of those rooms that were calling for heating this whole time or calling for cooling this whole time, now all of a sudden are driving it. So you have to be a little bit careful, because the goal is obviously not to just shift it, but to reduce it overall. So you have to do things like slowly, and that's why typically if you can do like a load management strategy to get ahead of it and just have controls in place such that, you are, like I know my boiler was coming on at a period of peak demand, so I'm going to change the strategy rather than, oh shit, I've reached my limit, I'm going to turn everything off, and then all of a sudden it's all going to turn back on again, and I'm going to have the same peak, it's just half an hour later, and now everyone's mad. So yeah, there's that.
Good stuff.
Okay, next slide. Any questions? Please feel to jump in, like questions. We got a small group. If you have questions, please let us know at any time. Yes?
Have either of you seen a building that's
Yeah, we've done quite a few.
She's in Canada.
I see the functionality built in, but I've never really seen the proof in the pudding.
Nor have I. In the US, I have not seen it implemented. Most utilities don't really support it in any way that's usable at this point in the US, to be honest with you. I feel like there are systems that can handle it, but just I don't know all the markets though. And these utility providers, they're all different. So each one's got, it's like, they is that how many? Yeah.
Wow, that's a lot.
So there's the ADR Alliance. Have you heard of that? So that's a format, but again, it's like, is it widely accepted? I don't know. So
Yeah. Oh, hold on. I was just going to say OpenADR, Canada's not as far in that, but we did a pilot program with OpenADR, and that is one of those things where it's like we're relaxing things just during that time, and then they just all ramp back up. So that's why I personally prefer the kind of like writing your sequences in a way that you are reducing your overall demand. But Brad did those, so go for it.
Yeah, I was just gonna say that, like thanks, Scott. The set point relaxing thing, I think in theory is a good idea. In practice, it's slow. Like it takes a while to actually lower the peak. So what I found is it's actually less effective than just like going into a speed drive and say like, I'm going to just take 10 or 20% off that speed drive set point, which we've done. You've got to be careful about, select the right drive that's not going to adversely impact things. But if you're careful, you can choose the right devices and load shed them. And I actually prefer that. I call it kind of like direct load shedding, where you're like directly reducing the speed drives.
Water pump, speed drives.
Yeah, or like capping the chiller. Yeah, just cap the chiller output, right? Like a lot of chillers will say, cap the reset on it to so you can't go to full capacity. That's actually more effective than doing the set point relaxing. The set point relaxing is less impactful in terms of the occupant experience, but and often like you're having to do like a quick response in terms of the load shedding because you've got maybe 10 minutes to respond before you incur that peak. So I don't find it to be as effective as just directly controlling it, but then you got to be really careful and not run into all the issues they just said.
Yeah, when we did the OpenADR, because it's, you're reducing in order to not pay that fee, right? So you do want to reduce during that specific time as denoted by your utility. So typically what I'll do is I'll go find like the biggest fans and the biggest pumps and the ones that'll make the most impact, and I'll reduce them to from 100 to 75. Not enough that it's really going to mess with things, but if they're big systems, like that can make a pretty big difference. And Brad's right, because even if you do reduce the set points, there may still be a couple that are driving it that were like way off set point to begin with. So they might still be driving your chilled water all the way down or driving your fan to max, even if the set points are reduced. So
I have a question.
yeah.
Are there, for both of you, when they talk about the smart grid, is it more than just ADR? And if so, what is the more in the smart grid conversation?
That feels like a Brad question.
Speak in the mic.
Thanks. Short answer is I don't know. I know, we're in British Columbia, so I know BC Hydro is now has an active load shed program. It's mainly for their peak, so it's like evenings, and they're giving like a day of advance notice. So it's not like an instantaneous response. It's like we know it's going to be cold tomorrow based on the weather forecast, and we historically know what that does to our grid. So in advance, we're going to ask for certain reductions, and they have a system that they're using, and I can't for the life of me remember the name of it, but it's not OpenADR, it's something else. And if I can look it up, I will.
Smart grid initiative.
Yeah, and it's not it's not real time. It's like, but that's a huge step forward for us. It's like a day in advance of, and they contract for certain demand reductions. So the buildings that sign up say, we'll give you 50 kilowatts or we'll give you 100 kilowatts, and they get a break on their bill because of that. But then they're obligated. If a call for power goes out, they're obligated to respond.
Got it. Thank you. Comment or question? Here, let me give you the mic.
Yeah, I can offer a little bit of U.S. perspective on that. So yes, you have, like in the U.S., these utility programs where a utility will say, you sign up, and if you respond during these events, like you'll either get a discount on your bill or you get some kind of payment for performance. That's one set of programs. You also have in a number of states and what they call balancing authority territories, wholesale participation program. So if you're a large load or you can aggregate a number of smaller loads, you can actually bid that into the wholesale market and actually get wholesale market revenue from that. So there's a number of different mechanisms. It gets kind of complicated, but those are options that you can explore sometimes with your customers. It really depends on where you are and who the different, like, some are state incentives, sometimes they're utility incentives, sometimes they're more regional based on the market operator. So it all depends.
That's awesome. Thanks. Yeah,
Thank
we're
you.
definitely a little bit behind on that because really only Ontario has time of day billing in Canada right now. But, we'll see it just shortly, I'm sure, and we'll get ahead of that.
I was wrong. They are using AHR.
Okay. Gotcha. Thank you.
Cool. Next slide. No more questions on that? Total tangent, but good one. All right. Scott, you're going to start this one.
I'm going to start this one. So sounds like we have some energy experts in the room, so I won't have to go into too much detail on this one. But really, when it's important to be able to monetize the usage, right? And the devices that you're using or you're trying to figure out how much it costs to use that device, say, it's not as hard as you may think. There's simply, it's just a matter of doing a little math, really. And I'm not going to do it because Stephanie's like a professor at this, and I'm going to do it wrong. So I'm going to let her do the math.
Yeah, I'm going to show you on the next slide. We'll do a little example. But just on measuring energy before we get into that, I mean, typically, in most cases, you'll have your utility meter directly connected, so you're just pulling it. And there are so many fancy ways that you can look at your energy and track your energy and baseline your energy. But like the easiest, I'm just going to skip for a second because I wanted this in a different order. But like this is a client, and I'm literally putting their data from their utility bill into a spreadsheet. Like it's not complicated. But just by looking at that, like I can be like, holy crap, what happened in 2022? And they hadn't noticed this because they're not tracking it. And I think the biggest thing I want to impress on you here is you don't have to have some fancy software, some EMIS, like some of those are, $80,000, $20,000 a year, like they're big spends. But just looking at that, like what happened here is they had a building automation system provider, they switched partway through, and so they kind of did a switchover of the system. And this big heat recovery chiller that they had was not properly commissioned as part of this setup. So now all of a sudden the gas boilers are the main source of heat. And so they were paying, first of all, for this like $2 million heat recovery chiller that was basically idle for a year. And now they're paying all of this gas. And so this whole year they weren't meeting their performance targets, and nobody knew until we came in to do an energy study. So this energy measurement piece, like doesn't need to be complicated. Now it can be, there's lots of ways you can do that, but just like looking at it is so key. And I always tell my clients, like just take a look at it, whether it's your utility bills and you can pull it directly in. I'm doing a sub-metering program with a client on a campus, so they don't have meters on every single building right now. They only have one for the 30 buildings on campus, and so they're doing sub-metering. I've seen lots of sub-meters on the floor. We use some of them. It's really complicated and they don't seem to realize that, and like the commissioning and having them communicate effectively, and then the battery dies and then it's offline and then the power goes down, and so that data gets lost. Like there's a lot that goes into sub-metering that makes it very complex. Now there's definitely still scenarios where it makes sense to put that in, but the other way you can get the data is from a building automation system. It's called virtual metering, and so basically I'm like, oh, I know my temperature in, my temperature out, I know my flow, I can calculate my BTUs of that system. Or I know my amperage of that, so I can calculate how much energy that's using. And so if you want a specific system, you just want to track the performance of that. Like, for example, this heat recovery chiller, I would have picked that up with virtual metering when I saw, oh, wow, it's like consumption went way down, its output. And so I would have caught that there as well. So there's lots of ways to track it. And it doesn't have to be some fancy EMIS, but just looking at it, would have saved this client thousands of dollars. So that's what I want to say about that. And we'll go back to this now here.
Yeah, to Stephanie's point, like any motor, anything that's drawing electricity will typically have like a plate on it that'll tell you the amp draw and the voltage, and then you just got to get the runtime on that thing, assuming it's running at 100%. And as she mentioned, you can safely guess what that thing's drawing from an electric basis. So
I might touch on this briefly because I'm getting the impression that the people in this room already know how to do this, but I've taught a couple classes on this for people who, aren't typically doing this. So what we've got on the side, and I have a little activity I'll show you because ChatGPT made it for me for my course, actually. But basically, it's like that light bulb. And if, you're an operator or you're working with an operator and they're trying to grasp this, you've got your, 100-watt light bulb. And so that's watts, but I want it in kilowatt hours. And then ultimately, I want it in dollars, right? So I'm going to take my watts, I'm going to convert it to kilowatts first. So I think they've just got it like right down here. Yep. So my 100-watt bulb is burning for 12 hours. So I'm going to take my watts and I'm going to multiply it by my time. And that's 240 kilowatt hours per year. And then I'm going to take my cost of electricity, and it costs $41 to run that light. Again, I know most of you probably know that, but it's not that complicated. And I've done this with a lot of people. I worked with a First Nations group to do this because they're not energy managers. They're like energy champions. And so they're, talking to people in residential spaces or in, their commercial spaces. And they're trying to get them to understand that it is worth it. And that myth that like, did any of your parents do that when you were growing up? It's like, don't turn the lights off and on. Like, it's better to just keep them on. Did anyone have that? I was like, I so thought that was a thing, literally until I taught this course and I Googled it. And so it used to be that with the old types of lights, there was a like surge of power when it turned on. So it was like kind of valid, assuming you were flickering it a bunch. But with LEDs, that's not really the case. And so I think if you're going to run it for more than like 1 second, it's worth it to just turn it off. Anyway, I myth busted that recently, and I was like, oh, wow. My whole life, I just totally thought that was a thing.
Yeah, and going back to like the example of a motor, when you're going to sell projects in the HVAC space, a lot of times they ask you for the payback. What's my payback? What's my payback? And of course, the number one payback in the HVAC industry is always going to be your energy, the energy savings you're creating. So even though you're getting electrical bills and you're getting subsidy, you have to be able to get granular with the energy usage, and you need to understand the formulas to support that. And that really is what this is talking about.
So I'm going to show you my example that I did with my students. And I literally, in ChatGPT, I was like, here's my course, make me an activity. And it did, and it was great. So just another usage of ChatGPT. If you were in the AI course earlier, if you weren't, look it up. It was so good. But basically, it literally wrote me this activity because what I was trying to get my students to understand, and this is often something when I'm working with clients that are maybe like less advanced in this space, less sophisticated, they're really stuck on the upfront cost. Like I'm going to put in an electric baseboard, not a heat pump, because electric baseboards are super cheap. And so what I was trying to get them to understand is that over the life of that baseboard, you're actually going to be spending way more money. And so this was the activity. So I basically said, let's calculate and compare the life cycle cost, not just the upfront cost, because that's where people get hung up, but actually the life cycle costs are what you want to look at. And I'll explain that in a second. I have this nice little activity. I'm not going to make you go through it, but these slides are all available on the Automated Buildings website. So if you do want to do the activity or share it with someone, or just make your own in ChatGPT, because, those are fun, you can. But basically I said, okay, I'm not going to get them to calculate how much energy they need from like a specific piece of equipment. I said, okay, you have to heat your home. It's 1,000 square feet. And in order to do that, that requires 200,000 kilowatt hours. Now, this was in Canada, so I said 720 gigajoules. Please, whatever conversion that is. I can't do those in my head. So someone can yell it out if they happen to know. But anyway, it was that much electricity or that much gas. So I was going to compare kind of options, electricity versus gas. So I told them how much energy they needed to produce. And then I said, these are your costs. We're not going to do time of day billing. We're not going to mess with that right now. This is a basic example. So this is how much you're paying for electricity. This is how much you're paying for gas. I did not update this for the States, so just bear with me. And then I gave them these formulas. So the life cycle cost, super basic, is how much you're going to spend initially plus how much you're going to spend every year for the life of the equipment. And then I'm going to add it together. So annual energy cost times lifespan. Then the annual energy cost is, well, how much I'm using times how much it costs. And then the energy input, energy output divided by the efficiency. So we're going to take the efficiencies into account here. And so I made this nice little table where you can go through, and the blue was what they had to do themselves. They had to calculate this. And again, I suspect that we don't need to go through this example, but I think what's really interesting here, I'm gonna go like this, is, so here's my electric baseboard. I have these in my rental house right now, and I will tell you that in my downstairs, it is 11 degrees Celsius, which is what? Like really, really cold.
50 something.
Yeah, like it's so cold down there because electric baseboards are insane. So it's $2,000 initially. It's super cheap as compared to a gas furnace, which is $5, and a split heat pump, which is $7. My efficiency of an electric baseboard is 100%. That's all electric, like pure electric equipment, 100%. Natural gas, we're assuming 90. Split heat pump, we're at 250. Now, obviously, that ranges based on outdoor air and all of that stuff, but we're basic example, so bear with me. And then we calculated our energy input, so just the output we needed, which I said was going to be the same, divided by the efficiency. We calculated how much it was going to cost a year. So look at these differences. $24,000 for the electric baseboards, like $3,000 for the gas furnace, and $9,000 for the heat pump. So that's one of those things, people put in electric baseboards in buildings that are cheap where people are paying for their own energy. But in your own house, if you're paying for the energy, it is not going to pay off. Like, look at this. Over the life cycle, I assumed 20-year lifespans for all of them, just to make it super easy. I'm paying like $500,000 for my electric baseboards as compared to $62,000 for a gas furnace and like $200,000 for a split heat pump. And so this is such a better argument to make because someone looks at the install, like upfront cost, that's including install, and they're like, oh, I'm definitely going to put in the baseboard. But they don't really think of the life cycle cost, which is, the most important part. And I think that's a big change we're starting to see in the industry. And this is how you're going to make your case, right? If you're like, hey, I have this sensor versus this sensor, and they're like, well, that one's more expensive. And it's like, well, this sensor is like more efficient and it's going to save you this. So if you can present that life cycle cost to them and get them thinking about that, it makes a really big difference. Anyway, I was shocked. And that's why my downstairs is so cold.
You keep the mic.
Okay.
Because you're like, I'm just going to run the slides for you. You're the expert, so.
Any questions so far? Who sells products? Who installs products? What does everyone else do? Design. Okay, cool. Just helpful. Thanks. So next slide. So anyway, that activity, I just literally asked ChatGPT to make me an activity. I told them like who my audience was and what their level of education was and what I wanted to get across, and it made me the activity, and it wrote it all out with like steps and break them into groups and do this, and it was great. So another use of AI.
Very cool.
Yeah.
Now we're going to talk about the way my dad used to do it. So
Yeah.
I'm second generation in the industry, and this was one of the first lessons my dad taught me. And this is really around the mechanical contractor in mind, but electrical contractor too. But the funny thing about it is that, as we mentioned before, the majority of the building's energy usage is going to come from HVAC and lighting. And one of the best ways to work with end users is to sell them energy savings programs, devices, things like that. But the worst thing to do is to sell them this stuff, but without baselining their current energy usage so they know what they save. So one of the things that we teach mechanical contractors at Cochrane Supply is essentially just how to go in and baseline a building, okay? And of course, we're not going to pick up like 100% of the energy, But we're gonna get a good idea of a good amount of the energy they're using just by evaluating the lights and the motors, okay? If you really think about it, HVAC, I mean, there's a lot of, I guess there's quite a bit of power draw on the controllers today, but if we're really trying to just focus in on the energy that HVAC is using, the motors are gonna be the majority of it. And so like my dad would literally go into a building, he'd find all the motors in the HVAC side, he'd get all the amperage, all the voltages, get all the run times, and then he'd go around and he'd literally count fixtures. I think he'd guesstimate number of fixtures, and he'd find out what types of bulbs they were. And then with that information, you're able to kind of get down to, with these types of calculations, you're picking up about 80% of about 60 to 70% of the energy usage in the building. And you can apply it against their rates, and this is just electrical. You can apply it against their electrical rate, and now you're gonna know how much are they spending per day, per year on that building for electricity, okay? And we're gonna get into ECM's, energy conservation measures, but now as you add your energy conservation measure, a lot of them are just cutting down on the time things are running. So now we simply change the time from 24 hours a day to say 12 hours a day. And if our current HVAC is running at $17,000 per day and we cut it by 12 hours, we're gonna cut the energy by 50%, folks. And they're literally, they're gonna save $7,000, $8,000 a day by doing that, okay? And as we talk to the owners, and we all know this, they need to justify their purchase. And as a good salesperson, if you're in the mechanical side, you should learn how to do this on the fly, while you're in front of the customer. It's so impressive if you can just kind of tell them, I'll bet your energy bill's about $10,000 per day. And they're like, how'd you know that? And then they're like, yeah. And then you're like, you're running 24/7? Yeah, well. Guys, that's a no-brainer. You don't even have to do much, right? So I think that the energy audit and establishing that baseline is really important, but bring real numbers, bring real facts with you when you do it.
Yeah, that's a great comment. When we do this, this breakdown obviously is going to be building dependent, but sometimes what I'll do too is if I don't want to get all the systems and I'm only going to affect a couple systems, like if your sensor or your motor or whatever is going to affect one system, you just pick that one and be like, okay, right now it's using that much. And 24/7 buildings are such a great example. I have never done an energy audit where I haven't found scheduling opportunities. It doesn't matter where the building is in their, how advanced they are with these strategies, because things change. It's oh, that was 24/7, but then the usage changed and we forgot to set it back. And oh, that was an override and we forgot to remove the override. Never have I not found scheduling opportunities. And they're, 10, 15% of your overall energy use can be saved with scheduling. So definitely look for things like that. That's huge. What we do to balance energy is we'll take the energy bills and then we'll take the major equipment, not the little ones. We'll kind of group that into other miscellaneous things like computers or cooking equipment, things that we're not going to touch in terms of energy opportunities. But we'll take all the major equipments and we'll balance them against each other. So sometimes, I'll be able to figure out what the schedule is, either from the BAS or from the operator. And then from there, I can estimate them and I kind of balance them to see how close I can get them. And that's how we would, baseline benchmark that building to see how much everything is using right now and how much savings we can expect.
The math will help you.
Use a spreadsheet and a calculator. I can't do math in my head. This is this. We already talked about this. But like I said, it doesn't have to be complicated. We actually do a lot of our work in spreadsheets. Seriously, we don't use the energy models. And we find often, because we work purely in retrofits, we don't do new builds, a spreadsheet-based model often works a lot better because I have the existing data and those models aren't set up for those as well. The energy models, I'm doing one right now where I'm validating this, and they gave me these numbers, and I was like, there's no way those are right. So I plugged the existing system into my little spreadsheet and I cross-reference them, and I'm like, no, your numbers are way off. So I find like people assume these energy models are better, and a lot of the programs, like, they require a fancy energy model, and they're not better. So, complicated is not always better. Just looking at it and having someone who knows and who can be like, some of our seniors, I'm like, oh, what should that number be? Oh, it should be 5. They'll just like, no, they've done it for 20 years. It's 5. So like having someone like that who can look at it and just being able to sanity check that. I do find for retrofits, sometimes like a spreadsheet based model where you're able to put in all the information because in a retrofit, so much, right? That you can't necessarily put into the model. So yeah, that's that. You may.
I think you hear the concept digital twin thrown around a lot, and I think digital twin often seems like a very intimidating, very high-minded, expensive concept to implement. But like what Stephanie just described is kind of like a DIY digital twin, because you're putting the equipment, you're getting a virtual representation of the equipment characteristics in a spreadsheet, but like then you can change those characteristics, change run hours. Maybe I want a smaller motor. I think I always use that as like a very practical example of like the power of a digital twin, and that a digital twin does not have to be, a really fancy piece of software with great graphics. It can be a spreadsheet, and like that's the kind of thing that you can do with it.
That's a good comment. I also am intimidated by the word digital twin, even though technically I do create them. But yeah, it always sounds intense and scary. So good comment. Thanks, Brett. Okay, is this me?
It's
You want to touch on it at all?
You can start.
All right. So energy efficiency. I teach a lot of courses on energy efficiency, and Scott said this. Do you want to say it? I won't steal it. You say your quote.
I had a couple of this. Okay, so this is, again, and my dad, he worked at Honeywell like in the 60s, so this goes way back. But the saying is, and this is from pneumatics, mind you, this was a pneumatic saying, the most efficient systems are the most comfortable. They're the most comfortable buildings. So the most comfortable buildings are the most efficient buildings. And does anybody want to guess why? Because if they're comfortable, more than likely they're meeting the design conditions it was intended for. And as such, that means that the building is using the right amount of energy to keep you comfortable, right? And so by nature of that, by using the right amount of energy for the application, it is the most efficient. Does that make sense? Is that fair? Anybody want to debate that one?
Capacity is well matched to load.
Yeah.
There you go.
Exactly.
That's another great way of saying it.
When efficient, we don't have excess capacity or not.
That's exactly right. We have to use energy, everybody. It's using the right amount at the right time.
Yeah,
That's where we're going to be the most efficient.
I totally stole that from Scott in my other session. I was like, someone told me this.
You can take it back to Canada.
I'm going to take it back to Canada. Thank you. Yeah, I always say like energy management and energy efficiency is really like turning things off when you don't need them and giving the right amount to what the demand needs. Match the capacity with the demand. It's really that simple. Like there's lots of complex strategies, AHR 36, blah, 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 that do that. But really all it is turning it off when you don't need it and, giving what is actually needed. So if, it's not that cold outside, you don't need to give it really, really hot water. Or if it's not that hot outside, your chilled water, your chiller doesn't need to work as hard. Or if there's only 25% of the people in the building, you don't need as much air, right? So it's that kind of stuff. That's really all it boils down to. Like setback control, turning it off, turning it down when it's not needed. If you have occupancy sensors or people counters, you can kind of adjust the load, adding the amount of fresh air you actually need. Demand control, we talked a lot about that, so maybe I won't touch on that in here, but really just scheduling. And like I said, scheduling is the most basic thing, and I always find opportunities in scheduling. I just did a building, and the other thing that's fun, if I see there's some designers back there, I always tell my juniors, they're like, oh, I looked at the schedule, it's working great. I'm like, well, the schedule could be great, but we got to look at the trends to see what it's actually doing, because so often the schedules are like, oh, perfect. And oh, it's been overridden. It's running 24/7. Or the nighttime setback is calling it, because the nighttime setback, and this I've seen this. We're doing a school district. There's 41 buildings. I think I've seen it in almost every building. The way the nighttime setback is controlled is as soon as the first room, one room in a building of like 100 rooms, as soon as one room drops below set point, the system turns on. So what I'm like is, okay, well, maybe let's wait for more than one room, or maybe we can do an average, or, it doesn't need to be that aggressive. Nobody's in there. So doing things like that, it's, the program looks fine, but if you actually look at the trends, it's on all the time. So just I tell them, never trust the schedules, never trust the pictures, always look at the trends to see what's actually happening, because that's where you're going to find those, there's lots of standard ones that everyone looks for. But there's also lots of weird ones. I didn't actually put any pictures in here, but, for example, I think I've done about 5 of these now, like water source heat pump loops. So it's a hydronic loop with water source heat pumps all in the spaces, and it's heated by a gas boiler, and it's cooled by a cooling tower. That's like not an uncommon system I'll see. And I have never gone into one of those and had it been working properly. It's always cycling, overshooting and then cooling, and then overshooting and then cooling. And I am actually recommissioned one just now, and I was like scratching my head for the longest time. I was like, why isn't this working? Like the flows should be correct. And I finally dove into the balancing report, and it was like the pressure was so high that the flows were not even close to what they were supposed to be. So every time the boiler would turn on, it would overshoot the system, and then the cooling tower would turn on, and they would just cycle on and off all day long. And so the people were comfortable because it was meeting set point. So that wasn't a trigger. But if you looked into the trends, you would be like, oh my goodness, what is happening here? But it takes someone going in and looking at those. So anyway, there's lots of complicated things to do. There's lots of standard things to check, like does your pressure reset? Does your temperature reset? Do you turn things off? Like those are the basic ones. But then there's also like, is shit being weird? So I also like to check those things.
What was that technical term again? No.
Very, very technical term. Yes.
So yeah, and so with building automation systems today, and with the amount of information that it's able to get back, we're seeing new strategies being developed through analytics and through the use of software. One of those new strategies we don't have listed here is the ability to do continuous commissioning with software and validate equipment runs, are doing what they're supposed to do. Going back to that concept of if we just run it according to the design conditions, everybody will be comfortable and will be efficient. And now with building automation systems, there are some that are actually starting to do real-time real-time commissioning, basically, of different applications. And NIST, National Institute of Standards Technology, they have now certified methods for doing that are available for different types of applications, including VAV. So a continuous commissioning algorithm for VAV, say, those are now available. And you can, if your BAS is connected and you have command and control over all of the inputs and outputs, you can start to do that type of thing. And while it's hard to guess the avoidance cost by something like that, what you can do, though, is you can guarantee a level of efficiency that nobody else can, which is another way to help you achieve more for your customers.
I love continuous commissioning. I have so many clients that are like, well, I get an incentive to do an energy study every 5 years. So I'm going to look at my building every 5 years, and I'm going to leave alone for 5 years. And during that time, guess what happens? The operators change things. They override things. And like for 4 of the 5 years, we're not meeting our performance targets. So I loved continuous commissioning. And I think as we start seeing these emissions thresholds and energy thresholds that are really common in the UK and in Australia and now in Vancouver and coming into place in Toronto, that really motivates people to stay on top of it and not just look at it once every 5 years. The one little word of caution with like fault detection systems, because there's a lot of them out there and they're great. Like, don't get me wrong, I've worked with lots of them, they're great. But I've had a couple instances where we've installed them and nobody had the time to look at them because the operators are like, well, I'm 2 people for 23 buildings. I don't have time to look at this. And, the energy managers maybe don't have the expertise. So nobody's really looking at them. And also, when you set them up and you don't configure them enough, you get all these nuisance alarms. So it's like every time I log in, there's 50 alarms. I don't know what to do. I get overwhelmed. I close it. And so what happened is we spent all this money setting it up. No one ever used it. And, we got rid of it. But then I have other clients who there's someone who takes ownership of that fault detection. Like, that's what they do. And they're sort of doing continuous commissioning. And that works great. But you really need someone with the expertise and the time to take ownership of what the fault detection system is saying and action it. Otherwise, it's kind of a waste.
Well, the worst thing is when they spend all that money on analytics, and they tie in their building automation system, they get all this stuff done, they got all these awesome charts, and then you look at what it's telling them, and it's telling them you didn't do your preventative maintenance. It's like, what'd you put in the analytics for when you weren't even doing your PM work? So I always tell people, man, before you go putting in a bunch of analytics, don't make yourself look bad. Make sure your PM work's done, right? Most buildings do not do their preventative maintenance work, which means that things like continuous commissioning and things like that, they won't work. We're in a physical universe. They got to go make sure that, the equipment's running on a schedule. That is a big part of it. It's not all about the computers and all the data. There is a physical component, preventative maintenance. It's really important in this too.
Yeah, it's funny how people think some new fancy software is going to fix it all and it's shiny and there's incentives and it's sparkly, and it's like you have to walk before you can run. You're really not set up for this yet. And I know that putting your energy history in a spreadsheet is not shiny and new, and doing your PM is not shiny and new, but that new, very expensive system is not going to work unless you've done the steps to get up there. So I have that all the time. Yeah.
I think alarm management is a major pain point with nearly every owner I work with.
Yep.
And I haven't seen a great alarm management program. I'm just curious. Have you worked with any facilities or campuses that had a deliberate approach to managing their alarms and making sure that the critical ones actually get attended to? I often see they're tuned too sensitively in the beginning. I do some new construction commissioning, and later it's so overwhelming if they do anything about it. Number one, they ignore everything. Number two, reduce sensitivity on all alarms. And either way, that intelligence, the good stuff, is not getting to the operators. And I'm just curious if you've seen best practices.
What an excellent question that is. Yes, that is definitely an issue. Scott, you want to chime in?
Sure. So it's kind of going back to what Stephanie just said. It's not about picking the right software to fix it. It's more about going back to the intent of the application design. And all these, pretty much any BAS system now can handle multi-factor alarming, right? So before we were really typically stuck with threshold alarms and things like that. But now, if specified or if asked for, we can add more variables to the alarming. And what our goal is of smart alarming is to essentially what you just, we're eliminating alarms, right? Duplicate alarms, ones that are redundant, things of that nature. I think if working with the integrators on your project or working with your design folks, and you specify what some of how you want it to operate in terms of those alarms, the newer systems can all accommodate it for the, you know what I mean? I don't think you can just throw a piece of software on a system that, when the contractor goes in, they set those alarms up in the construction phase, right? You almost have to rework every application if you put a new software in. So it's better to do it on the front side.
Yeah, it's not there's this one best practice. I don't have some really nice answer to give you, but what I find is that you get to the end of the project and the client's like, okay, we're done now. But trying to, impress upon them that this commissioning piece and this alarm management and getting it set up and dialed is really important, and not to end the project there. So what we've done is, sometimes we'll go through and we'll delete some of the standard alarms and we'll write our own rules for the alarms we actually care about, and then we'll only look at those. But it actually just takes time to look through some of those and train the operators on them. And like Scott said, getting rid of some of the ones that are duplicate, because if you log on to one and it's like you have 100 alarms, they're just going to close it. Like nothing's going to happen. Does anyone else have anything to add on that?
I was just going to add that, ASHRAE through Guideline 36 is also working on alarms, the hierarchical alarm suppression. So I think as we see that implemented, I think it's going to help as the vendors kind of implement that natively out of the box. I think some will start to adopt that. It's a step in the right direction. I don't think it's going to solve the whole problem, but it might take us from 200 alarms to unacknowledged alarms to 50.
I could see a language model helping out with that, Brad.
Ooh, there you go.
Just saying, SES.
AI.
There you go. All right, we're almost up.
Any other questions? Yeah, we have like 4 minutes, so we can just go to some questions or we can keep going. No questions? Okay. Oh.
I'll ask a question directly to Scott on this point.
Sure.
Okay, let's say you had a client today that wants to use a large language model to sort through the alarms. So would you say, yeah, we'd have to look into getting an API with the BAS, we could export that, then you sort through it outside of the BAS through a large language model, work with your IT team to do it, or what would be your, off the top of your head, possible setup? And I had a major healthcare provider ask me this same exact question. I'm just curious what your thoughts are.
So hasn't been invented yet. So hard to, and
okay.
I am not the expert on the technical side of it.
Just get the alarm lock to somewhere in LLM process.
Yeah, and I guess I have to defer it to Brad because he's put more into language models than I have. So I know the outputs of the BAS and the APIs, but I'm not sure if you could you hook an API directly up to a language model so that it streams into the language model? Do you know how to do that?
I don't know how to do it. I think what you said is like you'd get the alarm output.
Bring the alarms out.
Yeah.
I can do the other piece of streaming them into an LLM.
Yeah.
Oh,
yeah,
I
you can get
stream
the
them
alarm
out for
yeah.
you. So
You can
there you
get the
go.
alarms
We got a
out.
product. I'll stream them out for you. I know the API that's streaming them out.
Yeah.
You got it.
That's,
Deal.
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 That's doable.
Problem solved. Let's see me after. We'll invent a new product together. And yeah, I think a lot of people could use it, especially on existing jobs, right? So
I do work in software, although I'm a hardware engineer by training. Yes, you can stream stuff into an LLM. I think the thing I would worry about is what trained that LLM.
what? Who trained it, or what?
Yeah, what data set trained that LLM?
Right.
Right.
To the LLM,
Yeah.
the owner's needs.
Yeah,
It's not a.
It's a great idea.
Well working.
Yeah.
We could get
Right.
something working fast.
Yeah.
To get it good.
I take this more from kind of the energy, managing the grid services space, where you can get a long way just with kind of thinking through like a rules-based approach, kind of an if-then type of approach. Yeah.
Place the LLM.
Yeah,
you get most of the benefit without the added
Right.
complexity and the risk of hallucination.
Yeah, the concept of smart alarming is becoming popular, where they're actually adding analytics for alarming. So now we're, with analytics, we have a bunch of new functions that we can add to the algorithm to generate, again, very distinct alarms. So there's a lot of advancement in that right now to, again, limit the number of alarms. So another question in the back?
Yeah, I was just wondering about if this has to do with the peak management. If any of you have worked with like the energy storage systems. One of Tesla's biggest growing divisions is energy storage with power walls. And if either of you have been incorporating that in any of your designs or had questions from customers.
Yeah, we're doing a battery storage project right now. So we're doing that. And then obviously thermal storage is a lot for like domestic hot water heat pumps and things like that. What are our other storage ones? I know we have a partner working with phase change material. You can add to that.
Thanks. We're doing our first battery one right now. I'll say like our utility is incentivizing it now. Like they've got an active program to incentivize customers to look into battery storage and for their peak demand management. So going back to it's like when the utility has their peaks to say, go onto the battery for, and again, you've got to be able to provide so many kilowatt hours or so many kilowatts of load shedding for so long, and you're kind of under contract, but they'll pay for a good chunk of that battery system. Then you're free to use it for your own load management. Aside from that, I'd say we're really early days on it. Like I don't think we've got any lessons learned at this point. Like that project is in design right now, so maybe come back next year and we'll tell you how to make it work properly because we don't know yet.
Oh, yeah, we're out of time.
Yeah, thanks everyone for staying at the very end on Wednesday. Much appreciated.
Yeah, thank you, everybody. I hope you got some good nuggets out of this one. For those of you who've been at our other sessions, thank you for coming to other ones too. We appreciate you. Check us out on automatedbuildings.com. All these slides will be up there, and a lot of the other presentations we did, they'll all be up there probably next week sometime. We got to give Alicia a day to recover. I just want to do a quick thanks to Alicia and Josh, our production team. Yay, well done. Thank you guys, great job. And Brad, Stephanie, Carrie, good job team. Yay. Thank you guys. And we'll see you all next time. Take care.